Next speaker is Kasia Budzik. She'll tell us about holomorphic confinement and twisted holography.
Thank you. So I will talk about the holomorphic twist of n=1 superannuals and its holographic dual. So there have already been some talks by Davide Gaiotto and Justin Kalb at the previous meetings about n=1 superannuals. So today I will focus on the holographic dual. Okay, so the holomorphic twist of a 4D n=1 theory is defined as a cohomology of a supercharge. So 4D n=1 theories have 4 supercharges. So this Q cohomology captures the 1/4 BPS subsector. So for n=4 superannuals, this is the 1/16 BPS subsector. So these are precisely the operators that are counted by the supersymmetric index. Okay, and as the name suggests, the twisted theory is holomorphic. So we consider the theory in flat space, and we can pick some complex coordinates on C2. So with an appropriate choice of complex coordinates, one can check that the supercharges anti-commute to anti-holomorphic derivatives. Okay, so if we take cohomology with this Q, these anti-holomorphic derivatives are exact. So we end up with a 4D holomorphic theory. Okay, and it turns out that these holomorphic theories in higher dimensions, that they have a lot of interesting mathematical structure. For example, they have infinite-dimensional symmetry algebras, but I will not talk about this today. And finally, these holomorphically twisted theories, they appear as word volume theories of the three branes in topological B model. So one could try to study what is the holographic dual of this BPS subsector, and this has been called twisted holography. Okay, so the simplest theory we can study is a pure n=1 superannuals. So the theorem is that the holomorphic twist of this theory is equivalent to so-called holomorphic BF theory. Okay, so this is the action. There are two fields B and C. So they are superfields that are valued in anti-holomorphic forms. So they have some components that I'm not writing here. Okay, so the field constant of n=1 superannuals is just the vector multiplet. So we can match some of the fields of the vector multiplet with these fields of this holomorphic BF theory. So for example, this holomorphic part of the field strength is one of the components of B. And there are two gauginos, and they are components of derivatives of C. Okay, so the theorem is that the supercharged cohomology of this original theory is isomorphic to the BRST cohomology of this holomorphic BF theory. Okay, so this is like a simplified theory that captures the BPS subsector of this theory. Okay, so one of the things that we computed was the cohomology in the planar limit. So first, at 3 level, the planar limit cohomology has 3 towers of single trace operators. So these A and C are bosonic towers, and B is a fermionic tower. So like we said, derivatives of C were gauginos. So for example, C0 is the gaugino bilinear, which is in cohomology at 3 level. Okay, it turns out that this 3-level cohomology receives quantum corrections. So some of the operators that are BPS at 3 level are no longer BPS at the quantum level. Okay, so there's a one-loop differential which relates some of these operators. So for example, you can see the A and B towers, they are no longer closed, and these derivatives are exact. Okay, so the only operators that are still BPS at quantum level are this C tower that includes the gaugino bilinear. Okay, so one implication of this computation is that in particular the derivative of the stress tensor is exact. So the stress tensor of this holomorphic BF theory is the trace B del C. So you can see the one-loop differential makes this derivative exact. The derivative of the stress tensor generates action of certain holomorphic vector fields, for example, translations and rotations. So what happens is that at one loop, this theory basically becomes topological. So we call this phenomenon holomorphic confinement. So the holomorphic twist of n=1 superannuals is a topological theory. Okay, so now we would like to realize this theory in the topological B model. Okay, so let's consider n D3 branes in the B model in C3. Okay, and it turns out that the open string field theory on these D3 branes is precisely this 4D holomorphic BF theory that we were studying. Okay, so the topological B model has a nice closed string field theory, which is called the Kodaira-Spencer theory or BCOV theory. So the fields are polyvector fields. So these are anti-holomorphic forms valued in vector fields. So we can try to match this cohomology that we computed with the polyvector fields of the B model. Okay, so let's, for example, look at this one. So this is a distributional polyvector field. So let's say Z1, Z2 are the coordinates along the branes, and then Z3 is the transverse coordinate. Okay, so this is a delta function. So this is a polyvector field which is localized at a point at the brane, and it represents the insertion of the operator an. Okay, and analogously we can find the polyvector fields which represent the other towers. Okay, so now, we have these n D3 branes in flat space. Now we can try to back react them. Okay, so what happens is that this is not a geometric back reaction. So we are still in C3, but with the branes removed now. So what the back react in this D3 brane does is it sources a bivector field. So the effect that this bivector field has is that it introduces non-commutativity in spacetime. So these holomorphic coordinates Z1, Z2, they no longer commute, they commute to this. Okay, so another effect that this bivector field has is that it reduces the cohomology of these polyvector fields. Okay, so now the polyvector fields, alpha and beta, they are no longer closed, and the derivatives of these polyvector fields are exact. Okay, so this can be precisely matched with the one-loop computations we did on the gauge theory side. Okay, so to summarize, we conjecture that this holomorphic BF theory is dual to the BCOV theory in this bivector background. Okay, so this bivector introduces non-commutativity in the spacetime. And this phenomenon of holomorphic confinement that we observed in the gauge theory, so this was the fact that the derivative of the stress tensor was exact. We can see this holographically as the fact that this bivector background, it makes the BCOV theory topological. And in particular, we can precisely match the one-loop gauge theory computations with the back reaction of the branes. Okay, thank you.
Questions?
So why do you get on these branes the holomorphic twist of n equals 1 superigmals and not the holomorphic twist of n equals 4 superigmals?
So n equals 4 superigmals, the holomorphic twist of n equals 4 superigmals would be the three branes in C5. So there would be, it would be this holomorphic BF theory plus 3 beta gamma systems. And the gamma will be the fluctuations in the 3 transverse directions. And here we have only one transverse direction. So that's why we get D3 in C3 and not in C5.
So this correspondence with the BC theory is at one loop, or it's n equals 1 superigmals the full theory?
So the holomorphic twist of n equals 1 superigmals is the word volume of the D3 branes. And then you can match the one-loop computations in this theory, like supercharge one-loop corrections to the supercharge. You can match this with back reaction in the dual theory. This also the 3-level computations in n equals 1 superigmals correspond to just like B model not back reacted. And then the loop corrections correspond to back reacted.
So you believe the one-loop cohomology is the non-perturbative cohomology?
So there cannot be any correction. So the cohomology that we get at one loop is just the Cn they are all bosons. So if there was another like differential, it would relate fermions to bosons, but we only get bosons, so there cannot be any more corrections here.
Questions? Let's thank Kasia again.